last time we introduced the coarse-grained Landau free energy, and the partition function could be written in terms of this trace over all these order parameter fields in real space, and this sum over the exponential factor e to the minus beta L, where L is the coarse-grained Landau's free energy. And we start from this formula then, and we try to evaluate this partition function based on the coarse-grained order parameter, which we call the eta here. And for a finite size system, this trace is nothing but the product of the finite integral over the eta I, where eta I represents the coarse-grained variable. But now we try to go to continuum limit by setting this lattice constant to 0, and the number of particles goes to infinity, but the volume keeps finite. Okay, so in that continuum limit, this kind of discrete integration over this coarse-grained cluster is actually written in terms of the infinite product of infinite terms of this integration over this continuous variable eta of I, or eta of R, and this kind of infinite terms in the product of this order parameter field could be rewritten in terms of the Fourier integral, okay, or the integration in the momentum or Fourier space. Okay, so because we could easily Fourier transform this order parameter from the real space, continuous variable R, to the inverse space, which is the momentum space or wave number space, by this Fourier transformation. So we could easily translate or transform this kind of infinite terms in the integration over continuous variable eta of R in terms of the product of this kind of momentum sum. And the sum over momentum actually ranges from, say, plus minus, say, a 1 over lattice spacing, which is lambda here. But we could take advantage of the symmetry between this real part of the eta minus k and also imaginary part of the eta minus k. So we could just restrict our phase space to just half of them because there's a relation between this eta k and eta minus k. So then we restrict our integration to the positive values of momentum k, which we call this trace prime. Okay, so we start from this Fourier integration of this coarse-grained variables for this partition function, and in this continuous limit, or even in the discrete limit, we are able to calculate various correlation functions. For example, this kind of a spin-spin correlator, eta I, eta j average, which can be expressed in terms of the functional derivative of this partition function with respect to this external field Hi and Hj on different sites, I and j, and divided by this beta square and this partition function. So you could easily verify this identity by taking this derivative of this partition function written here for a finite system, and if you take the second derivative of the z with respect to the h, then you get this correlator, right? Okay, so that's the discrete version of this correlation function that could be derived from the so-called functional differentiation, so which we'll define in just a moment. But in the continuum limit, which we often call this in the field theory, that z, the partition function, is written in terms of this continuous integration over a continuous variable eta as a function of R, and the external field, instead of a discretized field, we consider a continuous distribution of the external field, H of R. And the coarse-grained Landau's free energy could also be written in terms of this continuous variables eta as function of R, and we simply just replace this discrete label eta of I to a continuous labeling eta as function of R, right? By taking the continuum limit. Okay, but when we take the continuum limit, we are able to define so-called functional differentiation and to get the corresponding correlation functions by taking the functional derivative of this partition function with respect to this external continuous field. And to that end, we defined so-called functional derivative remember now this partition function, or the free energy, is actually not just a function but a functional. Okay, so let me just spend a little time to actually formally define what this function is and functional means. Okay, so a function is actually dependence on the variable x, and x is just independent variables. But the functional, you can consider this as a function of function. Okay, so the f function is a function of y, but the y function is a function of x. So the f function is a functional of y and also x. Okay, so and this precisely fits this form of this partition function, because the partition function is a function of eta, and eta is a function of the spatial coordinate r, and therefore the partition function is a functional, okay, which is a function of a function. So we are familiar with the derivative of a function, but we haven't formally defined or studied the functional derivative, okay, which is very similar in spirit to the ordinary differentiation, but now we should remember that the function that we take the derivative is actually not just a function but a functional. So the formal definition of a functional derivative is here, that we call this delta f by delta eta, where this delta refers to this variation of this functional. Okay, so the variation of functional is defined by the kind of a difference between this functional taking a slightly different point away from the original variable eta at position r. So this eta of r is actually shifted by a slight amount, which we call this epsilon amount. And this delta function is actually the guarantee that this is actually happens when this r equals to r prime. And we need to subtract by this original functional at the original place, eta of r, and divide by this difference values of the eta functions, and taking the limit of the epsilon goes 0. So it's simply just kind of a generalization of ordinary differentiation for ordinary function of x. Okay, so we could actually use the following identities to define this functional derivative. For example, if I take the functional derivative of this integral with respect to eta, and we should get 1. If you take this eta differentiation with respect to the eta of r prime at different place, we get delta function. This gradient square of eta, if you integrate over this entire r prime, and you take the function derivatives of this integral with respect to the eta of r, you get by this kind of a integration by parts, it's given by minus gradient square eta of r. So and so on and so forth. You could simply check this by using your knowledge in calculus. Okay, so if I calculate this deviations of this functional f, which is the free energy that is derived from the partition function, and this partition function is calculated through the cross-grained Landau's free energy. Okay, so this delta f is given by this kind of expression value of this order parameter in the continuum limit times small variations of the external field. So it's called the linear response. So after linear response, this ensemble average, or the average order parameter, or expression value of the order parameter, is given by this kind of a functional derivatives, delta f divided by delta h. Okay, you simply just move the right-hand side of the equation to the left-hand side, and you can define ensemble average of your order parameter in a continuum limit. So likewise, by the way, this is nothing but the magnetization. And the isotomal spin susceptibility, which is the functional derivative of the eta with respect to the external field. So in other words, you could actually expand this definition of this eta average, and so this chi t is now a second derivative of this free energy with respect to this external field, which we will describe in just a moment. This is a more general formalism beyond this Ising model, where we are able to calculate any correlation functions once we know this coarse-grained Landau free energy functional, and we can use that to compute the partition function and take the functional derivative, and you get various correlation functions that you want. Okay, so let's take a short break. So we just defined this variation in this functional differentiation context, and also we define this isotomal spin susceptibility in this functional derivative, which is the second order derivative of free energy with respect to this external field. And remember that this chi t depends on two different position vectors, r and r prime, and where this r and r primes are at different locations. And what we would like to see here is that what is the relation between the spin r and the spins at r prime. And the relation or the correlation between these two spins at different locations could be calculated by this chi t. So in other words, the second order derivative free energy is back to this h and another h at different position r prime. Remember that. So I call this h and h prime. So and then you could use this free energy as minus kBt log z, and you plug that in back to this second derivative, and you could just clean up all these different terms of the second order differentiation, and you get two terms. And if you evaluate this first term, this is nothing but correlation function of two spins at different locations, r and r prime, okay, which is what we defined earlier. If you simply just take the second derivative of z with respect to h and h prime and divide it by z. And what about the second term? Well, the second term is nothing but the product of the two expectation value of the order parameter, which is the first derivative of z with respect to the h and divided by z. So this is the definition of this order parameter ensemble average or expectation value of the order parameter at r and also at r prime. So in other words, you get two terms which subtract from each other. So the first term is the two-point correlation function or spin-spin correlation function. The second term is actually the square of the average order parameter. Okay? So by definition, this is what we already defined as the Green's function or the correlation function g as function of r and r prime. And there's a prefactor beta, which is 1 over kBt here. So well, you could easily verify this definition. Okay? So in other words, the isotomal spin susceptibility is nothing but linearly proportional to two-point correlation function or the Green's function, g. So now we try to evaluate this Green's function or the isotomal susceptibility both in real space and in K space. So suppose our system is actually translational invariant. So that this, it doesn't matter where this, these 2 points are, but the important point is that this function depends only on the distance or the difference between these two vectors r and r prime. And then we can easily see that this correlation function g is actually linearly dependent on this isotomal spin susceptibility, and you know that this spin susceptibility is actually a response to your external field. It's a response function of the magnetization to the external field. In other words, the response function is actually linearly proportional to the correlation function g, and we call that this is a linear response function, or in the linear response theory. So we could Fourier transform this real space linear response relations between g and chi, and to the Fourier space, to the K space. So this can be done by simply just Fourier transforming the coordinate to the K space variable. In K space, the Green's function is actually a function of K, and the chi also is a function of K. So we can also write down this kind of response function and in K space and define the isotomal susceptibility in K space. We simply just Fourier transform all the variables from the real space to momentum space. And a particular interesting quantity of isotomal susceptibility is so-called static spin susceptibility, where you take k equals 0 in this general chi t as function of k, and this limits when k goes to 0 of this chi t is the same as beta times g of k, but you take k equals 0. But what is this gk0? Well, gk0 is nothing but integration over the real space Green's function, and that is equivalent to take spatial average of your correlation function. So remember, the static susceptibility is nothing but the spatial average of your correlation function. And we will get back to this soon. So now we can compute this g as function of r from the mean field theory within the Landau formalism. So first of all, we should find out this mean field value for this order parameter eta by minimizing this Landau's free energy with respect to the eta variables, and we set this differentiation to be 0, and remember this is the functional derivative. And if we do so, then we get this equation here, but this is not what we want. We really want this chi of t, but the chi of t is actually the derivative of this eta with respect to the external field at different positions. So we simply just take the functional derivatives equation 1 and with respect to the external field, but this external field is at different place. So now we can simply just plug in this equation 1 here and take the functional derivative of equation 1 with respect to the external field, and we get to that equation. But on the right hand side of the equation, it is a Dirac delta function. Okay, so now we could take advantage of the relation between chi and g. We can simply just rewrite this equation in terms of the Green's function or correlation function, and then we arrive this equation. And this is a very important equation which tells us how this g behaves. So we can solve this sort of a differential equation, and we get the g as function of r. So let's solve this differential equation for our Green's function or two-point correlation function GRR prime. We could divide this calculation into two parts. First, when temperature is above Tc, and second, when temperature is below Tc. Okay, so when temperature is above Tc, we know that there is no order parameter, where the order parameter is actually 0. Therefore, we simply just get rid of this eta in this equation, and we could just rewrite our differential equation in terms of a minus gradient square plus so-called c greater to the power of minus 2, and altogether multiplied by this Green's function is actually given by kbt divided by this gamma times delta function. So where this c greater is defined by gamma divided by 2at, and taking the square root of that. Okay, well, little t is defined as what, t minus tc divided by tc. Later, we'll show that this c greater or c lesser is actually nothing but the correlation length, okay, which diverges as temperature approaches Tc, and this divergent exponent is actually t to the minus nu greater, and nu greater here is actually 1/2. Okay, so this is inverse 1/2 power in t, which is the divergent power for the c. But at this point, we don't know the correct interpretation of this c. At this point, we don't know what this is, but this is simply just some kind of a new variable which I just call this c. All right, okay, so we're almost there. But for temperature below Tc, when little t is negative, we know that there is a finite magnetization or order parameter developed which is at plus minus square root of minus at divided by b, which we derived some time ago, right? From this minimization of this Landau's free energy is back to this phi or eta, and you can see this global minimum point. And you plug in this value of eta back to this differential equation, you get another one which is very similar to this equation above Tc, where we define this C lesser variable, which is again the correlation length for temperature below Tc. And it has almost the same form as T greater, except the prefactor is different. The prefactor is actually a quarter, but this prefactor for C greater is actually 1/2 inside the square root. And so, but again, the power law is the same. It's T to the minus 1/2 power, and here we define this new minus, which is the correlation length exponent, as it is 1/2 here below Tc, and nu plus or nu greater is the same value. It has the same value, 1/2. So we'll show just later over there that this C is nothing but correlation length, which diverges at the transition. But now let's solve this G as function of R. In any case, we need to solve this equation, which is minus gradient squared plus C to the power of minus 2 times G is actually a Dirac delta function multiplied by this kBt divided by gamma. Okay, so we can Fourier transform this differential equation, and we can easily solve that in k-space. So this Laplacian, when we Fourier transform this, is nothing but k squared or minus k squared. So now this gk could be easily derived, which is you can simply just move the other prefactor on the left-hand side of the equation to the right side. You get this k-space solution for this Green's function. Sounds familiar. So it's like a Yukawa potential in Coulomb interacting electron gas. But remember, we have such a relation that gk is actually kBt times chi t. And let's look at the solution at the transition temperature, T equals Tc. And we know that from this previous over there, we get C plus, C greater, C lesser both approach infinity, but this 1 over C goes to 0. So at the transition temperature, so this C to the power of minus 2 is gone. So you get just a very simple k-space representation of this G at the Tc. And when gk is 1 over k squared, you can easily Fourier transform this to real space representation of this Green's function, which is 1 over r to the power of d minus 2. Okay, so this is correct behavior in real space when dimensionality is actually above 2. So when d is actually above 2, then this Green's function in real space behave like this at the transition. So now, before we continue our calculation to temperature above Tc or below Tc, we can show that the C plus or C minus or C greater, C lesser variables that we defined over there has the correct interpretation of the correlation length. So again, we should make use of this relation between this Green's function and this susceptibility function temperature at k equals 0. So when k equals 0, this is gone. This isotomal susceptibility is nothing but C squared divided by this prefactor gamma. But we know what this is, because from this mean field calculation, the Landau theory, we know that this is given by 1 over t, 1 over little t. So we know this is the result coming from the mean field theory of Landau formalism. Okay? And putting this formal form, which is t to the power of minus gamma, where gamma is actually 1. Remember that. Okay? We obtain such a 1 over t behavior in isothermal susceptibility when we calculate Landau by the mean field approach. So now we immediately get this c squared is actually proportional to 1 over t. And therefore, c is actually t to the power of minus 2. And from this expression, we immediately see that this has the correct interpretation of the correlation lens because it diverges, and because we know that from the isothermal susceptibility near this transition, and C squared is actually proportional to 1 over T near the transition when this little t is actually very, very small. So therefore, this behavior is actually has the correct interpretation of the correlation lens. And so we could safely say that this C is actually proportional to its divergent as little t to the power of minus nu, where nu is called correlation lens exponent. And because we know this relation between Green's function and the susceptibility, and also we know the susceptibility when temperature is close to Tc is 1 over little t. And therefore, we know that the C is actually proportional to t to the minus nu, or nu is plus 1/2. So now we complete the circle that C greater and lesser defined over there have the correct interpretation of the correlation lens, which diverges at the transition. So now let's take a short break. When we come back, we will continue calculating the Green's function away from this transition temperature Tc. So to solve for the Green's function for a general temperature T not equal to Tc, we need to solve this differential equation again. But it is more convenient to solve this equation in the polar coordinate by writing down this so-called radial equation, okay? Because this equation has this kind of a spherical symmetry, so it's better to use this polar coordinate, okay? So we plug in this polar coordinate for this gradient square, and also this replacing the vector r as a radial vector in this kind of a polar coordinate or spherical coordinate. And we define this dimensionless quantity rho, which is r divided by this correlation lens c. And then we plug in this differential equation, this polar coordinate, and we get this second order differential equation like this. So this is very much like the radial equation for the hydrogen atom under the Coulomb interactions in 3 dimensions. And we define this little g as a function of rho as this Green's function as a function of this dimensionless quantity r divided by this correlation lens. And this little g is a constant which is given by this, and later we will interpret this as kind of dimensionless strength of fluctuations. So we will explain to you why we call this little g constant as dimensionless strength of fluctuations. It is a dimensionless quantity, and it has the meaning of strength of fluctuations, beyond this Landau's mean field theory. So, but in any case, we could use that newly defined variables to find a solution, and the solution is simply just a spherical Bessel function, Kn as function of a rho, and g as function of rho is given by this, little g strength of fluctuations times this 2 different functions depending on this dimensionality. When this is 1 dimension, this is e to the minus rho. When this is above 1 dimension, say 2 or 3 dimensions, and this is given by a power law in rho multiplied by this spherical Bessel function, k is function of rho. And I'm writing down some kind of asymptotic behavior of this spherical Bessel function in both when this r over c is actually infinity, or r over c approaches 0, and or when d is actually 2, or this little n is actually 0. So you got the logarithmic dependence on rho for this k0 rho. Okay, so you could just transform this rho back to this r over c, and we could write down this final expression for the correlation function in these 2 cases when this distance r is actually well above the correlation lens, or when this correlation lens almost diverges. So you get 2 different behaviors depending on where you are. So if you are away from this critical temperature, then it is the first top equation or solution that this g of r obeys. But if you are very close to transition temperature, then it is a second equation or a second solution expressions, is the solution. Of course, you need to be at dimension which is above 2. Okay, I guess that's about this mathematics or this computation of a Green's function, the correlation function, which is roughly speaking this kind of a spin-spin correlation. And this Green's function is a very powerful function. It's a very useful function which allows us to prove these correlations of our interests. For example, the spin-spin correlation or the current-current correlation in the charged material, or any correlation you could think of, for example, the superconducting correlations or superfluid correlation, and so on and so forth. So let me just summarize. So today we introduced the functional derivative method to calculate the partition function, and the partition function is written or expressed in terms of the Cosgrand Landau's free energy density, and this kind of functional formalism or functional differentiation allows us to compute various correlation functions which can be measured in real experiments. And that concludes this kind of a mean field approach based on the Landau theory. And starting next lecture, we will discuss the fluctuations beyond Landau's mean field approach. And we'll see that this kind of a prediction makes sense only when temperature is actually not that close to the transition temperature. If the T is too close to Tc, then these fluctuations beyond Landau's mean field approximations takes place. Okay, and then we need to modify this Landau's free energy and to actually address these fluctuations beyond the mean field approximation. Okay, so things will get more and more interesting because now we get into these technical details of how we could compute and we can understand the phase transition. This comes to the heart of the phase transition and critical phenomena, and also statistical field theory. So I'll see you on next Monday.